Okay, yeah, Kelvin, absolutely, absolutely. And well, John's working on it, but he'll get there. Joe, all right. Yeah, Rodrigo, all right, you'll get there, Rodrigo. Well, we're going to try to make, you might have, how many have noticed that there seems to be maybe, thank you, Sebastian, how many have noticed that there seems to be a pattern when they find the derivatives of different polynomials? How many are kind of, for instance, seeing a pattern, maybe? Yeah, Nicholas knows what I'm talking about. Ian does. Yeah, there's almost, you can almost get like to where you could almost guess what the derivative is going to be. And that's what this first example is. Yes, Rodrigo agrees. So you've learned about using the definition of the derivative to find derivatives of different functions, and now you're going to be getting some general formulas for derivatives of functions in chapter 3. And in section 3.1, we focus on derivatives of polynomials and exponential functions. So take a moment to copy that down. Copy the example down. Okay. Okay. So we're going to show that based on the definition of a derivative, the limit definition, that the derivative of x equals 1, the derivative of x squared equals 2x, and the derivative of x cubed equals 3x squared. And what I'm using here is, this is called Leibniz notation. This is called Leibniz notation. d dx means take a derivative. That's what d dx is symbolic for. And after we find these, after we prove this, we want to see if there's a pattern. Let me ask you, given that these are true, what would the derivative of x to the fourth be, based on the pattern you're seeing here? That's right, everybody, 4x cubed. Very good. So let's go ahead and proceed to the work this out. Thank you, everybody. So if our function f of x equals x, okay, if our function of x equals x, f prime of x, of course, using the definition, is the limit of f of x plus h minus f of x over h. But our function here is x plus h. Okay, that's our function. All right, because if f of x equals f, x plus h is, of course, f of x plus h. And then, of course, the x is equal to f of x. Well, what happens is, of course, the x's cancel, and you're left with the limit as, actually, this should be as h approaches 0. I have a little typo here. Hold on. This should be the limit as h approaches 0. And h over h is just 1. So the limit of 1 as h approaches 0 is 1. And so therefore, we say that the derivative of x with respect to x, that's how we, like if I read this statement, we say the derivative of x with respect to x equals 1. Okay. All right, are there any questions on this? So what we're doing is we're going to try to come up with a general formula for the derivative of x to some power. And you know, there is a general proof of this, but we're going to intuitively do a few examples and intuitively arrive to what the formula is. Okay. All right. Next, our function f of x is equal to x squared. So we use the definition again. So f of x plus h is x plus h squared right here. And f of x is x squared. And we work through the definition. So hopefully everybody's comfortable. Of course, nice things have to happen to compute this limit. So the x squareds cancel out. And so the f prime of x is the limit as h approaches 0 of 2xh plus h squared over h. And then we can divide the h, simplify the h out. So we get the limit as h goes to 0 of 2x plus h. And therefore, that's just going to give us 2x. This means then that, and I'll state the statement here, the derivative of x squared with respect to x equals 2x. Okay, so not too hard to confirm these. Are there any questions so far? All right. Well, let's move on then if everybody's good. Now we have f of x equals x cubed. Same thing. We're going to use the definition of the derivative and evaluate. And I know that you've worked with these kind of expressions. X plus h cubed can be shown to be x cubed plus 3x squared h plus 3xh squared plus h cubed. Okay. You know, if you take x plus h and multiply it by the x squared plus 2xh plus h squared, because x plus h quantity squared is x squared plus 2xh plus h squared. You know, that you just work it out, you know. I mean, you've done this before. You've done this before. Okay, and some good things happen, of course. Some nice things happen here. That's what's so beautiful, you know. This beautiful stuff happens. And then we divide the h through, and we will get 3x squared. And so therefore, the derivative of x cubed with respect to x equals 3x squared. Okay, and we can intuitively say, based on this pattern we're observing, that the derivative of x to the fourth with respect to x would be 4x cubed. Okay, we can say that, which some of you already were very comfortable with. What about the derivative with respect to x of x to the fifth? What would that be? Ah, okay, 5x to the fourth. Good. Good. All right, and so, well, are there any questions so far? All right. So what we're now, you know, now we are going to come up with a formula for the derivative of x to a power that we can use to help us find our derivatives. So we are moving away from using the definition of the derivative to find a derivative of a function towards deriving formulas and using the formulas. And the formula here is this one. There's a pattern, and you've pretty much guessed the pattern. If n is a positive integer, the derivative of x to the nth power with respect to x is equal to n times x to the n minus first power. And this is a formula that you can use in chapter 3. You can't use it in chapter 2. Okay, you can't use, like the last exam, you can't use that formula, right? Because chapter 2, you're using the definition of the derivative to compute your derivatives. But for chapter 3 problems, you can use this formula. And in fact, they show in the book how they get the formula, the general formula, and they use something called the binomial. They use something called the binomial theorem, which some of you might have seen in the past, but maybe not all of you. But at any rate, you have an appreciation for this formula. It makes sense that it's right, and we're going to go with that for now. But you're welcome to look at the formal proof of this is what's called the power rule. You're welcome to look at that proof in the book, the formal proof. So this is we basically feel comfortable that the derivative of x to the nth power with respect to x would equal n times x to the n minus first power. We're comfortable with that when n is an integer. But in fact, it can be shown that if n is any real number, like a fraction, any number, a fraction, for instance, a decimal, the derivative of x to the nth power with respect to x will equal n times x to the n minus first. I agree, Sebastian. It's an amazing rule, amazing rule. And they'll in section 3.7, they prove this general result later in chapter 7. In chapter 3, section 3.7. And Neil's right. It makes it a lot easier. But also, I look at it like you've all, in a way, earned the right to use a formula, because you know how to use the definition of the derivative to find a derivative. You know what it means intuitively and geometrically, finding a derivative. Now it's time to gravitate towards using some formulas. We're maturing here. Of course, you're welcome to do the old-fashioned way, but how many kind of like using some formulas for chapter 3? How many think that's kind of cool? Okay, Neil likes formulas. John likes formulas. Rodrigo, Joe. So Nicholas, ddx. This ddx is notation. This ddx is notation. It means take the derivative, ddx. So this last statement here means we say it as this very last statement here. I'll put the arrow by it. Means the derivative of x to the nth power with respect to x equals n times x to the n minus first power. That's what that means. All right, Shaco, Sebastian, Rodrigo. Okay, you're welcome, Nicholas. You all like the new rule. Okay, great. Great. Well, would you like to learn some other rules? How many would like to learn some other rules for derivatives? Okay, a lot of you. All right, all right. Well, all right. We just learned the power rule. Let's proceed on then. Let's proceed on. Are there any questions? Okay. Well, here's a rule. Here's a rule. that says if you take the derivative of a constant times a function, if you take the derivative of a constant times a function, that equals the constant times the derivative of the function. Let me give you a moment to copy it down. Okay, so again, this rule says that if we take the derivative of a constant c times a function f, that'll equal the constant times the derivative of the function. That's what that says. So how would we have to prove this? This is a general result. C can be any constant. What would we have to do to prove this result, to formally prove it? What would we have to use? What definition would we have to use? Well, there's no power rule here. There's no x to the nth power here. This function f of x, thank you for your answers, Lynn and John. This function f of x could be any function. It could be a cosine function. It could be a square root. Well, it could be, you know, e to the x. It could be anything. That's right. We need, as John Levin says, definition of a derivative. That's how we have to prove it. But once we use the definition of derivative to prove this general result, thank you, Sebastian, that's right. Once we use the definition of a derivative to prove this general result here, this formula, then we're going to use the formula in the future. So, okay. Well, what I'm going to do is I'm going to define this constant times my function x as a function g of x. I mean, a constant times a function of x is a function of x, so I'll just call it g of x. So g prime of x then, okay, would be, I mean, it would be the limit as h approaches 0 of g of x plus h minus g of x. Well, g of x plus h would be the constant times f of x plus h. And g of x is the constant times f of x. Okay, are there any questions up to this point right here, up to that point right there? All right. Well, absolutely, it's cool, Nicholas. I agree. Okay, Trevor, very good. So, yeah, well, we notice that there's a constant here, and the constant can be factored out. But then that constant can then be factored out in front of the limit as well. Giving us that g prime of x is just the constant times f prime of x. So what I did, John, is the function I'm trying to find the derivative for. Okay, John's wondering why we let g of x equals c times f of x. So I am trying to get a formula. Okay, hold on here. Yeah, I'm trying to get a formula for a constant times f of x. And I'll make just a comment here. I'm using like the bracket symbols for grouping just because you know it helps make things clear. But in WebAssign, remember, WebAssign usually does not like for answers where you have grouping symbols. It doesn't like these brackets. It likes parentheses over the brackets. How many have noticed that in their answers? It likes parentheses. WebAssign likes parentheses. Sure, Trevor knows, Joe knows, Nicholas knows. But of course, then John knows. But of course, when you're talking about interval notation, you know, then sometimes you know you have to use brackets. That's a whole different thing. But okay, so what I'm doing here, is I'm trying to find the derivative of a constant times f of x with respect to x. Well, it's okay, isn't it, that I call the constant times f of x g of x? I mean, I can do that, right? And by doing that, it just makes it a little easier to you know, write down the definition of the derivative here. Makes it just a little bit easier. That's all. I mean, I could have gone right to right to this step here. Okay, but like I could have gone from here right there to that step. But it's a little nicer just letting the constant times f of x equal g of x. John, are you comfortable with that? Okay, excellent. And now, okay, so g prime of x, which was the derivative of a constant times f of x with respect to x, that equals the constant times f prime of x, right? Which is the same, by the way, as the constant times d dx of f of x. Because f prime of x it means take the derivative. F prime of x means take the derivative of the function with respect to x. Oh, well, that's what this means too, right? So hence you get your result. Okay. Yes, I agree, Sebastian. Very interesting. And we're going to be using that rule. We're going to be using this new rule later today. You know, I don't know what that rule's called, Ian. Well, actually, I do. The book calls it the constant multiple rule. I'll write it here. probably a good idea to give it a name. This is called the, maybe I can put it in black here, the constant multiple rule. Because you're taking the function and you're multiplying it by a constant, and then you want to take the derivative. Constant multiple rule. Getting better with this mouse, getting better. Okay. All right, are there any questions before we move on? How many would like to learn a few more rules? All right. All right, all right, well, let's go to the next rule. John, this is all meant to make it easy for you, absolutely. Okay, now here's something you've done before. You've had to take derivatives of polynomials using the definition of the derivative. Okay, thank you, everybody. Well, what we want to show here is that the derivative of a sum of two functions is the sum of their derivatives. Let me give you a moment to copy the rule down. Okay, so again, the derivative of the way we write this, like we can write this way if we wanted to use briefer notation. F plus G prime equals F prime plus G prime. That's a quick way. That's a quick way to denote that rule. And this, by the way, is what's called the sum rule. The book calls this the sum rule. Incidentally, if you had instead of F plus G prime, if you had, let's try to get this right now. If you had F minus G prime, what do you think that would equal? That's right, Lynn. That's right. That's right, Betsua, John, Nicholas, Chaco. Absolutely, very good. And I don't know why that thing showed there. I don't know why that line shows, but we're not going to worry about it. Yeah, that would just be F prime minus g prime. So that would be then the difference rule, right? But we're just gonna show that the sum rule, and then you can take it on faith that the difference rule would follow. And actually, it would make sense because f minus g, remember, you can write it as f plus a negative g. So essentially, the difference of two functions can always be written as the sum of two functions. As, you know, f minus g is f plus negative g, and then you can use the sum rule. All right, so let's move on here. Let's look at the proof. Now what we're going to do in the proof is we're going to let big f of x, my big f of x function, capital F of x, be equal to the sum of my little f and g functions. And I'm interested in f prime of x. I want to know what the derivative of x is. Oh, no, I'm sorry. I want to know what the derivative of my capital F function is with respect to x. And so naturally, we go right away to the definition of a derivative. And that would take you to this step. Big F doesn't mean derivative. No, good question, John. All I'm doing is I'm defining here my f plus g, the sum of these two functions, as another function. And the other function is capital F of x. It doesn't mean actually it doesn't mean derivative, it doesn't mean antiderivative. Now in section 2.8, when you had a little function f, the big F would be standard notation for the antiderivative. So in a way, the big F is not maybe the best notation, but it's what actually they use in the book. And it's okay, you know. All right, so we're going to use the definition of a derivative. And then we write out what big F of x plus h is. And we write out what big F of x is. And then we're going to subtract the little function f and g and rewrite the quotient this way. And I can split the fraction up into the sum of these two fractions here. I mean, we can do that. And then the limit of the sum is the sum of the limits. Let me give you a moment to catch up here, but hopefully the steps seem intuitive. And then you get f prime of x plus g prime of x. So the derivative of our capital F function with respect to x is equal to f prime of x plus g prime of x. And that proves the rule. That proves this sum rule. Yeah, it is pretty cool, Sebastian. I agree. Absolutely cool. Are there any questions on how we derive this result? Are there any questions at all? Okay, excellent, excellent. Well, then the um, the rule then holds. The rule holds, and now we got another rule that we can use. Let's see. Nicholas says, do derivatives just follow the limit laws? They have to. That's right, Nicholas. They have to. Let me go. So you notice here, like you had like in this step here, and I'll go back to that next page, but you had the limit of a sum. You had the limit of a sum. Well, the limit of the sum is the sum of the limits, assuming both limits exist. And when we say that f and g are differentiable, that means the derivatives exist. Derivatives exist for f and g. So the derivatives have to follow the limit laws because they are. A derivative is defined as a limit. F prime of x is the limit of f of x plus h minus f of x all divided by h. So yeah. You're welcome. All right. Now the book, of course, has a lot of good examples, and I'm going to do some examples. I'm going to add to the variety of examples. One of the examples I'm doing is from the book, but the other two will add to the variety that you have in the book. I'll just mention this. There is an example 8. No, hold on. There is an example 3 that talks about equation of tangent line and normal lines to a curve. And that's an example you'll have to look at. You'll have a homework problem on that. But let's proceed. That's example 3 from the textbook. But let's proceed to the examples that I picked out. Okay, take a moment to copy this example down. Okay, so in this problem, we want to find the points on the curve. The curve is this polynomial, y equals x to the fourth minus 6x squared plus 4. We want to find the points on that curve where the tangent line is horizontal. And when they mean tangent line, they mean tangent line to the curve. Okay, that's what they mean. So let me just, they just say tangent line, but they mean tangent line to the curve. This is actually example 6 that I'm working here from the book. So we want to find the points on the curve, y equals x to the fourth minus 6x squared plus 4, where the tangent line to the curve, you can insert to the curve there, where the tangent line to the curve is horizontal. Now what we're going to do is we're going to draw a picture and see how many points there would be. Notice it says points. Okay, points. So we'll go to the solution. First thing I do is I draw the function x to the fourth minus 6x squared plus 4. This is an even function, by the way. It's an even function. I mean, here, this is the origin here, right? But f of negative x would equal f of x. How many remember even functions from pre-calculus? Yeah. Very good. Very good. And so f of x equals f of negative x equals f of x. If you substitute in negative x for x, you're just going to get back the function, the same function. And so the values of the function to the right of the origin, where x is positive, would equal the values of the function to the left of the origin, where the x is negative. And so you have this symmetric even function about the y-axis. And based on the picture here, there are 3 coordinates on the curve where the tangent line to the curve is horizontal. And we need to find these 3 points. So what do we have to do? I mean, find the derivative. That's right. Sorry. Just making it. Find the derivative and get the zeros. And by the way, what's the slope? Hold on here. What's the slope of each of these horizontal tangents? That's right, Kelvin. Good. 0. So I'm going to take the derivative of my function and set the derivative equal to 0. And that'll tell me what x values correspond to the slopes of the tangent lines being equal to 0. So, okay, we have to find the derivative. Are there any questions so far? All right. Good. Well, we have to find the derivative of this polynomial. And normally, back in chapter 2, you would use to find the derivative of that polynomial, you would use the limit, you would use the definition of the derivative, and you would compute a limit. And it would involve like x plus h raised to the 4th power, x plus h squared raised to the 2nd power, and so forth. And you'd have to work out the algebra, and it would take some time. But because we've learned some new rules for finding derivatives, we can utilize those rules. So the first rule, what are, like, let me think about like the rules that we've learned here. Maybe so we know that the derivative of f plus g equals f prime plus g prime. Would it make sense that the derivative then, so that's the sum rule. The derivative of a sum is the sum of the derivatives. Could we extend that rule so that the derivative of the sum of f plus g plus h equals f prime plus g prime plus h prime? I mean, do you think it would make sense that we could extend that rule? Absolutely. Absolutely. And that's what we did here on this step. We have the derivative of a sum. Well, there's a minus there too, but the minus also it works. So on this first step, I mean, are there any questions on? I just applied the sum rule on this first step here. That's what I did. Are there any questions? Who's feeling very comfortable? And by the way, I'm using Leibniz notation because it makes it easier to keep my work organized. And this is the kind of work you'll need to have for your next exam, exam 2. This is the kind of work you would be showing. All right, so step by step. Well, now, very good. Now the next step is to apply our rules. So the derivative of x to the 4th is 4 times x to the 4 minus 1 power. What rule did we use there when we took the derivative of x to the 4th? And got 4 times x to the 4 minus 1 power. That's the power rule. Very good. Okay, that's nice. And then the derivative of 6x squared, okay, the derivative of 6x squared is equal to 6 times the derivative of x squared. What rule did we use there? Where we factor the 6 out. That's right, the constant, the multiple, oh, I have it here. You're right, the constant multiple rule. The constant multiple rule. And the last one, the derivative of the constant 4 equals 0. So if you were to have a function y equals 4, what's interesting about the function y equals 4, if you graph y equals 4? What do you notice about it? It has a slope of 0. That's right, Nicholas. It's flat. It's a horizontal line. And the derivative of a horizontal line with respect to x would be just plain 0. Doesn't matter what the x is. It equals 0. So that gets us to that step. Are there any questions so far? Okay, well, now we're going to apply the power rule to the derivative of x squared. Okay, we're going to apply that power rule to the derivative of x squared, and that gets us 2 times x to the 2 minus first power. And so the derivative then is going to, the derivative of x to the 4th minus 6x squared plus 4 with respect to x, that's going to equal 4x cubed minus 12x. So to find the x values, we need to find all the x values where the derivative is equal to 0. Because when the derivative equals 0, that's when the tangent lines to the curve are flat. They're horizontal. So let's make sure, I'll give you a moment to copy here. And if you have any questions, please ask. Okay. How many like taking their derivatives this way, using the rules? How many like that? Okay, wow, a lot of positive responses there. All right. Well, now you've earned the right to do that. All right, excellent, excellent. So in chapter 3, you can do that. And so now what we have to do is we have to solve the equation 4x cubed minus 12x equals 0. All right, I'll move to the next page. So, all right, now we never want to divide by the variable. We want to factor the left-hand side. So 4x is the least common denominator. And then you have 4x times x squared minus 3. And x squared minus 3 factors into x minus root 3, x plus root 3, giving us our 3x values. X is 0, that's one value. We know that because 0, 4, that point, there's a horizontal tangent. X equals root 3 is another value, and then x equals negative root 3. And that would make sense because it's an even function. So if the tangent line is to the curve is flat when x equals root 3, you know, if it's horizontal at x equals root 3, then another tangent line at x equals negative root 3 would also have to be horizontal. And therefore, our given curve has horizontal tangents when x equals 0, x equals root 3, and x equals negative root 3. And then these are your corresponding points. 0, 4, negative root 3, negative 5, and negative root 3, negative 5. And obviously, yeah, I agree, Nicholas. It's excellent. And obviously, you know, this -5 here on the coordinate, what I did was you have to substitute in -√3 into the function x, right? Or you know that. So I didn't work it all out, you know, but that's how you get the value. Oh, thank you. There's a typo here. There should be a yep. We should have a positive here. Thank you. Good catch, Nicholas and Ian. Right. Hold on here. We'll fix that right now. There we go. See, you're getting good. I think you're in test mode. You were being very careful, and that's good. That's one thing that my tests do. I mean, that's another bonus. It teaches you to try to be careful. Nothing wrong with that. But of course, on the free response exercises, I gave 2 attempts because we're human, right? And so what I did was the function the curve, okay, hold on here. The curve is equal to x to the 4th minus 6x squared. Okay, good question being asked, plus 4. And so, like this, if we do f of positive √3, you'll get √3 raised to the 4th minus 6 times √3 squared plus 4. And I want to keep this all, separate here. Okay. And this is going to equal 9 minus 6 times 3 plus 4. And that's going to get you, what, 13 minus 18? That's going to get you -5. That's how I got the -5 here. Okay, you're welcome, Ian. You're welcome. Because they were asking about what points on the curve. Now, incidentally, I had a question for you. Suppose, well, let me. Are there any other questions before we move on here? All right. Question for you. Suppose that suppose you had a similar problem, and let's say you took a derivative. Actually, hold on. Let me bring up the the whiteboard real quick. Okay, so suppose that your f prime of x, suppose you had a similar problem. And, you know, f prime of x were equal to something like, you know, 12x cubed minus 7x squared plus 4x minus 5. Okay, let's say you had something like that. And so you had to solve that polynomial equation. How would you do that? And by the way, I know in pre-calculus you learned like the rational root theorem. How many recall that? Where you could find rational roots and candidates and then find out which one works, you know, P over Q. How many remember the rational root theorem? Okay, so kinda, how many does it bring back a memory? You must have seen it if you're taking pre-calculus at Montgomery College. All right, well, at any rate, you're not going to need to use that, and I don't want you to use that. Okay, so, yeah, if you just go into Google, type rational root theorem, you'll see it. But for this, just to solve it, let's say it can't be factored. What would you have to do? What would you have to do to find the zeros of this function? You know, how would you find the zeros? How would you find that? Well, you know, Nicholas, I want something easier than that. The last problem, we could factor it and it worked well. But how would you have to do this one? What if you were to graph this? What if you were to graph this? And, you know, let's just suppose, let's just suppose, and I'm making a guess here, let's just suppose it looks like that, okay? Actually, hold on, might be worth, let me just try it here. I'm not going to go through the whole problem, but I'm trying to bring something to your attention. But what I'd like to do is draw a graph that maybe that will, at least in theory, be like the graph of this 12x cubed minus 7x squared plus 4x minus 5. So let me just see here. Hold on. One moment. Hold on, everybody. Well, all right. I'm not getting this. I don't want to digress here. I don't want to digress here. But let's say that, you know, you have a function f prime of x, and it's going to equal to ax cubed. I'm not saying this the way I want to say it. Let me say it again. Let's say that f prime of x, I'll be a little more general, equals ax cubed plus bx squared plus cx plus d. And you want to set that equal to 0, just like we did in the previous problem. And let's say that A, B, and C are such that the numbers are such that that this is what, when you graph that polynomial, this is what it looks like. You're graphing the derivative. How would you find the x values, you know, where your derivative equals 0? Before, we were able to algebraically do it. How would you do it using your calculator? You want to use your calculator. What feature on the calculator would you have to use? You could do a trace bits to it, but it still isn't going to give you the value. You'll be able to approximate it. You could do, that's right, Lynn, the intercepts or the zeros. So remember, on your calculator, if you go to second calc, there's a feature called 0. Or intersect is more for, I thought intersect was more for like if you have two different functions intersecting each other. But on the calculator, you would use the 0 feature on your TI. How many recall doing that in pre-calculus? I mean, you must have. I've taught pre-calculus. Sure. So just use the 0 feature in your TI. And Joe, if you have not seen it, you just go to Google and say, you know, finding zeros using TI calculator, using your TI 83, 84 calculator. I think in the homework there's a, sure, you're welcome. I think there's a, like a watch it video for this, but I just wanted to kind of prepare you. Okay, well, let's continue here. Let's continue. Okay. All right. Here, my function v is equal to square root of x plus 1 over the cube root of x, quantity squared. And I want to find v prime. All right, let me give you a moment to copy that. Okay. So, well, we can't use the power rule on this. Even though we do have a squared power here, we have a sum inside. So we can't use the power rule on this function. And, you know, we have to work with the rules that we learned. So what might be something we should do here, you know, to help us with this problem? What might be a good thing to do? Expanded. Very good, Lynn. Very good, James. We want to expand that because we can't use any of the rules. And you know, there's something called the chain rule, by the way, but you're not going to learn that till Wednesday. So, all right, we're gonna expand this. So let's go to the solution. All right, but you know, before I expand, I will take the cube root of x. Well, Lynn, I wanted to do a kind of a tough one with you, a hard one. You know, in your homework, there are going to be some problems where you know, there's like 20 some questions in your homework for Wednesday, and some questions will go pretty quickly getting the answer, but you know, others are going to take a little more effort, right? And I wanted to do one that you're welcome, Lynn. That would I guess I wanted to do a scary one, for lack of a better word. But it's not scary, is it? Nobody's scared, are they? So, okay, Rodrigo. All right. Well, let's see if we can help you here. So first of all, to use the power rule, I want powers. All right. I think Sebastian Rodrigo, when we're done, hopefully you'll be less scared. The cube root of x I can write as x to the third. And 1 over x to the third, okay, 1 over x to the third, I can write as x to the negative third. Okay. So this is all, you know, standard algebra that you've learned, pre-calculus stuff. And I'm gonna, you know, I know that I'm gonna be wanting to use the power rule here. So let me turn, like also you notice the square root of x, I wrote as x to the half. If I'm gonna apply the power rule for derivatives, then I have to rewrite this function v. You notice I'm not taking the derivative yet. I'm gonna rewrite the function v so that it's in a nice form. And then once it's in the nice form, then I'll take the derivative. Okay, so at this stage here, all right, I'll just write x to the half power plus x to the negative third power squared, the quantity squared. I'll just expand that out and do FOIL on it. So what I'm doing is I'm getting the function, I'm rewriting the function so that I can apply my derivative rules. All right, let me give you a moment to catch up here. Let me know if you have any questions. Okay, so as you know, a plus b, and I do see another hand there. We shouldn't have that hand there. A plus b quantity squared is a squared plus 2ab plus b squared. And that's what I've used here. But now we know that when we have the same base, what do we do with the exponents when we have the same base? You know, x to the half times x to the half. What would we do with those exponents? We would add them. And a half plus a half equals 1. Similarly, x to the half times x to the negative third. I add the half and the negative third. I'm going to get 1/6. And then x to the negative third times x to the negative third gives me x to the negative 2/3. And so now my function v, right, this is the first power here, right? My function v is in a good form now to take the derivative. Now I'm going to take the derivative, because I can apply the rules that I know to get the derivative. So v prime is the derivative of v with respect to x. I always like to bring in that Leibniz notation when I take my derivatives, because it just helps reinforce the rules. Well, I mean, of course, I know the rules pretty well, but what I'm trying to say is I'm thinking in terms of you all as students learning these rules. The Leibniz notation is very helpful. How many like the Leibniz notation, the ddx notation? Yeah. Nicholas likes it, Neil likes it, John and Betsua, and you know, you have these different ways, notations, because they're useful to make things clear in different situations. Well, the derivative of a sum of functions is the sum of the derivatives of the functions. And that x is x to the first, right? And then you just apply the rule, your rules, 3 rules. Derivative of x to the first is just 1. Well, it's what it is formally, right, is 1 times x to the 1 minus 1 power. But x to the 1 minus 1 power is x to the 0th power. That's just 1. So, you know, we use the sum rule here. And now we're doing the derivative of each of these functions. The 2 for the second derivative, by the constant multiple rule, the 2 gets pulled out of the derivative. And then the third part, the derivative of x to the negative 2/3, I'm just applying the power rule. So this problem, you're using the sum rule and the power rule and the constant multiple rule. And by using Leibniz notation, you're able to really show those rules being used, applying those rules that are new to you, right? So you want to use this notation. You want to do the problems this way, really to help you learn these rules. All right, and then I use the power rule again on the derivative of x to the 6th power with respect to x. And then I finally get the answer. We finally get the answer. All right, are there any questions? How many of you would hate to use the definition of the derivative to find this derivative? Okay. All right. You'd have a lot of conjugates to worry about, I guess, on this. All right, so derivative rules make our life easier in chapter 3. Are there any questions before? Yeah, that's right, Neil. It would be a lot of conjugates involved. That's right. Would not be pretty. So some of these problems in your WebAssign, you'll have to, you know, before you just go and try to take the derivative, try to get the problems simplified out before you take the derivative. All right. Are there any other questions before we move on? Okay. Let's do one more here. All right. I'll let you copy this example down. Okay, so on this problem, you're being asked at what point on this curve, y equals 1 plus 2 times e to the x minus 3x, is the tangent line parallel to the line 3x minus y equals 5. No, and Nicholas saying, could we set the y's equal to each other? All that would tell you is where the trying to solve it would tell you where the two curves intersect, but they may not intersect. They may not intersect. We're interested in you know, when they mention tangent line, when tangent line is mentioned in a problem, what do you think of finding? Slope. And slope is the same as, well, what's another word for slope in calculus? Derivative. Very good. Very good, Lynn. Very good, Betsua. So what we have to do, since they're saying at what point on the curve is the tangent line parallel to this line, they're talking about tangent lines to the curve. So that means we have to find the derivative of this function, 1 plus 2 times e to the x minus 3 to the x. We have to find the derivatives. So to that, and then let us proceed on. So again, here we have the derivative of the sum. Y prime is the derivative of the sum of these three functions. That's going to be the sum of the derivatives. And using the rules that we learned, we get there. Now there's one rule that we need here to do this problem. What's the derivative of the exponential function? It turns out it's going to be itself. The derivative of the exponential function is actually the exponential function. And that is that's a rule that right now you're just gonna take it on faith. But we can do a little better than that. If we were to draw e to the x, okay, this is f of x equals e to the x. And then we were to draw some tangents at different points to the curve, different points. Okay. So, you know, like I have 3 x values that I picked here, and I drew tangent lines to my function e to the x at those x values. Yeah, I drew tangent lines to the curve f of x equals e to the x power for these, you know, 3 x values. And what do you notice about the slopes of the tangent lines as x increases? As x increases, you know, as you go from the first x value to the second x value to the third x value, the slopes increase. That's right. Excellent, everybody. The slopes increase. And they increase at the rate of increase is e to the x power. So the derivative has to be a function that's increasing, and in fact, it's e to the x power. And it only works, Nicholas, it works with e to the x power. To my knowledge, I want to be careful here because I don't like to generalize, but I'm you know, the kind of the most famous function I know whose derivative is equal to itself is e to the x power. And this is just a little I always like to give you intuitive feel for things. So this is why then when we take the derivative of e to the x, we can replace it with e to the x. That's what. So that's another rule. That's yet another rule. Very cool, very cool. And so now y prime is going to equal 2 times e to the x minus 3. But we're interested in the problem about, you know, that's our tangent. That's the slope, right? This is the slope. Of the tangent. Of the tangent. Okay. at x. Okay. And we want to know when that tangent is parallel to the line 3x minus y equals 5. Well, in order to do that, we need to figure out what the slope is of 3x minus y equals 5. But that's easy. That's a line. You just get it in slope-intercept form. And you'll see that the slope of the line is going to equal, it's going to be m equals 3. 3 over 1, right, which is 3. So when a tangent line to our curve has a slope of 3, it will be parallel to the line y equals 3x minus 5. Okay, of course, we're not done yet, but what do we have to set? What do we have to set? Oh, sorry, hold on here. Yeah, we have to set our derivative. Very good, everybody. We have to set our derivative equal to that slope. All right, so I'll move to the next page if we're all good. We'll be able to have some time for you to work a little bit today on your on the new homework, and of course I'll activate the the old assignments, the exam remediations after class. But all right, any questions? Okay, so we set y prime equal to 3 and solve for x. So 2x minus 3 equals 3. That means, I'm sorry, 2 times e to the x minus 3 equals 3. So 2 times e to the x equals 6. Therefore, e to the x equals 3. And it's an exponential equation, so you take the log of both sides. X equals log of 3. And so therefore, I'll give you a moment to catch up here. So x equals log 3, that's at the point then when x is log 3, but they want coordinates, so you got to figure out the y. Well, this is what y would be. It would be, remember what y was. Y was equal to, what was y equal to? 1 plus 2 times e to the x minus 3x. So then when x is log 3, you're going to have 1 plus 2 times e to the log 3 minus 3 log 3, which that y coordinate will be 7 minus 3 log 3. So at that point, the tangent line to our curve will be parallel to the line 3x minus y equals 5. And this is just a picture where they show our curve. Right, they show the curve here. Y equals 1 plus 2 times e to the x minus 3x. And they have the line here, y equals 3 minus 5. And you'll notice when x equals log of 3, when x equals log of 3 is, let me see, this is the point. Hold on here. This is the point right here. The log of 3 is basically, let me see, hold on. The natural log of 3 is about 1.0, it's 1.09. So that's like right here, 1.09. And they draw tangent line when x equals the log of 3, right here. And you can see that that tangent line to the curve is parallel to the tangent line, tangent line to the curve at this point when x equals log 3 is parallel to the line y equals 3x minus 5. So that's just a nice description there, nice picture. And incidentally, this here, y equals 3x plus 7 minus 6 times the log of 3, all they did there was they found the equation of that tangent line using the point slope formula, where your slope is 3 and your point that that tangent line passes through is the log of 3, and then 7 minus 3 log of 3. So they left out some steps, but that's how they get that. So, you know, this problem, it's a good problem because it really, you know, I want you to do more than just be able to use the rules and find derivatives. I want you to be able to think conceptually as well. And this will be useful for later in the course and your future courses. All right, are there any questions at all? Any questions at all on this problem? All right, good. And just a reminder, in the book, there is an example 3 in your textbook that deals with tangent lines and something called the normal line. Normal lines are perpendicular to tangent lines. And the example 3 in the book, they work out the problem nicely. You should, when you work it on your, there'll be an exercise in section 3.1. It's one of the, it's actually one of the earlier ones where they, like a tutorial one, and it follows example 3 in the book. So I think it's maybe the second question or the first question. At any rate, example 3. You'll want to look at that. Okay, let me stop the recording.